Hello everybody, my name is Eugenio Lomurno and I'm a PhD researcher from Politecnico di Milano, and today I have the pleasure to present you our work named Pareto-Optimal Progressive Neural Architecture Search, which is a research in the field of automatic machine learning. Before beginning, I want to present you our research team, which is composed by me, my colleague Stefano Samele, and our teachers Matteo Matteucci and Danilo Ardagna. This work has been financed by the European Commission through the Horizon 2020 project, and it is part of the iSprint project. So, why is nowadays necessary to automate the neural architecture search? Well, first of all, because not always good human being intuitions lead to good architectures, and also because the human effort is not predictable. So, neural architecture search comes as a solution to this issue, with the goal of automating the neural network architecture generation through a maximization of the expected accuracy. And its results are really competitive. In some cases, they reach the best human being capabilities, and in some cases, they are able also to produce better architectures. So, for instance, when we think about neural architecture search, we think about the cloud, because basically it requires a lot of efforts in terms of computability. But this can be very expensive, and also the code is not available like the final models obtained. So the goal of our research is to produce a scalable framework for the neural architecture search in order to face this issue and to allow the users to produce their own neural architecture search also outside the cloud. In order to do this, we identify a trade-off between the time and the accuracy, so that we can meet the user needs also in cases there are time constraints or limitations in terms of computation. So we are following this approach. Basically, we choose a proper neural architecture search algorithm as a starting point, and then we introduce a time predictor to evaluate the training time of the generated architectures. And finally, we compare the best results from this approach to the results obtained with the original algorithm. As neural architecture search algorithm, we have chosen the progressive neural architecture search, which is basically a recent algorithm that exploits a simple to complex approach, producing at the beginning shallow networks and trying to improve the performance by improving their depth until some convergence is reached. It is based on a controller network that in this case is an LSTM, with the goal of evaluating the accuracy performance of the generated child networks. In this case, we are dealing with CNNs, and so we will have convolutional layers and pooling layers. So the idea is the following. We have cells that are composed by units that we call blocks. Each block is composed by two inputs that in our case comes from the previous cell. Each input has an operation that has to be searched by our algorithm. In our case, we will deal with convolutions and pooling operations. And finally, we have another kind of operation which has the goal to combine the outcome of the two previous operations. In our case, we have chosen the concatenation. So we can describe the entire problem under two main points of views. The first is the macro architecture search, which is the number of cells composed by these blocks which have to be stacked. Then we have the microarchitecture search, which is basically the research of the best internal structure for each cell in terms of number of blocks and in terms of structure of the single blocks. The idea is more or less the following. So in this picture you can see the cell HC-1, which is the input of the current cell, that is composed by 5 blocks, each one which their operation, their concatenation, and finally we have a global concatenation which creates the input of the next cell. So the idea behind the Pareto-Optimal progressive neural architecture search is basically to keep all the advantages of POPNAS, but this time we want to select the architectures belonging to the Pareto front, which is built over a time and accuracy constraint, which will lead to all the architectures with the same accuracy but with minor training time. So the algorithm can be summarized as follows. So, as we said before, we are using a simple to complex approach, which means that basically we start with cells composed by only one block. We train and evaluate them and we fit the controller. Then we expand them to all the possible permutations of operations in terms of convolutional layers and tooling layers, and we evaluate them in terms of accuracy and training time. Then we cut out all the solutions outside a time limit L, and we select the top key best architectures from the Pareto front. We repeat this step until we reach the desired number of blocks for each cell. The challenges that we have to face following this approach are basically two. The first one is that each cell during the iteration has a variable feature number. This means that we start, of course, with only the features related to the single block, and at the end of the research we have the features related to all the blocks inside the cell. Then we have to predict time performances from features that have never been seen before, because the time predictor receives as input the information related to the previous steps of the research. In order to solve these problems, we have extended all the cells up to B blocks. This means that even when we have one single block, we still have the features related to the next blocks, but basically they are all set to 0. And we consider them as unused. Then we feed our time predictors with the number of blocks, the inputs, and the operators in a first instance. But given that we feed for each cell all the blocks with the same input, we have decided that due to redundancy it is preferable to remove these features from the training set of our time predictors. To further improve our approach, we have conducted some ablation study. This is, for instance, what we have called dynamic operator index, which is basically an ordering among the operations we have chosen for our approach, in order to have that the operations which require less time are selected as first operations. As you can see, we have chosen an index based on the normalized time which is required by each operation. So by this way we are now able to rank our operations according to an index, and also through this technique we can set the index of the unused blocks to 0, which is just a way to let the models understand that blocks are not used at all. Another problem we had to face is the initialization of our algorithm, that in this case has been solved by what we call the initial trust improvement, that basically is a cell composed by all known operations. And this is because each cell receives as input the output of the previous cell. So after this initial trust, we have created the thing that we called sliding block mechanism, which is basically a technique to represent the same cell in different ways, and this is used to evenly distribute all the observations among all the blocks in the cell. We have also conducted an ablation study to select which are, according to our purposes, the best time predictors. In details, we tried 3 different machine learning algorithms and an heuristic method that we called block sum. We tried this over an NVIDIA Tesla V100 GPU, and we used the starting algorithm that we have described before, POPNAS, and we tested our approach over a fold of the CIFAR10 dataset. As you can see, the image represents the real time and the predicted ones, and for instance, the most left points represents the predictions where the number of blocks is equal to 2. According to these results, we have chosen to select the 2 most performing algorithms, which are actually the ridge regression and the NNLS algorithm. In this slide, you can see the performance of the ridge regression with the input, as I told before, the cell input, and without the input and with the dynamic reordered index. Actually, the results are not improved for the ridge regression, but for the NNLS, we can see a quite important improvement. And so, for this reason, we have selected the NNLS as the algorithm to use in POPNAS experiments, as you can see from the improvements in the lower part of the table. So, finally, after the ablation studies, we have reached the final part of our experiments that are the comparison between the POPNAS and the PNAS algorithms over another fold of the CIFAR10 dataset with a number of blocks per cell equal to 5 and a number of stacked cells equal to 3. We have computed both the algorithms over a GeForce GTX 1080 Titan. The image represents the real times and the predicted time, like in the images just seen before. And from the tables, we can see that for b equal to 5, POPNAS reaches the lowest error over time predictors. Actually, in this image, we can see the predictions of the POPNAS algorithm, and the green line represents the Pareto front in which we are gonna search our best architectures. So, as you can see, there are huge improvements in terms of time, both for b equal to 2 and for b equal to 5. In orange, you can see the PNAS top key selections, while in red, you can see the POPNAS ones. Regarding instead the children network accuracies, the best performances are reached with b equal to 5. And so now we can go to the final comparison. Looking at the table, which represents the top 1 network found by the 2 algorithms, we can see that despite an accuracy reduction of 9.6%, our algorithm was able to find a network which has a time training boosting of 173.7%. Finally, we compared the entire execution time of the 2 approaches, and as you can see from the table, POPNAS was able to achieve a time boosting of 204.9% with respect to the PNAS. So, in conclusion, in this work we propose POPNAS, which is a scalable neural architecture search algorithm that starts from PNAS and is able to handle efficiently a trade-off between the training time and the accuracy of the children network, and has the Pareto efficiency property. As next steps, we plan to extend the domain of our algorithm and also to enlarge the search space to different layers, operation, and architectures. I want to thank you for your attention, and if there are questions, I will be happy to answer. Thank you.